The Michelson interferometer was used in an important experiment by Michelson and Morley that was meant to resolve a problem in physics. The problem was that Maxwell, we'll remember, had calculated that light could only travel at one speed in a vacuum. This created problems with a long-held idea called Galilean relativity, which you have already used when it comes to working out the addition of velocities. To illustrate the idea, if a man throws a ball towards you at 8 meters per second, then it travels towards you at 8 meters per second. However, if he is standing on a truck that is moving towards you at 15 meters per second, and he throws the ball at 8 meters per second, that means the ball will actually be approaching you at 23 meters per second because you had to add those velocities together. So relative to him, the velocity was 8. Relative to you, it's 23. However, what if he was shining a torch at you? The light would be leaving him at c, the speed of light. But don't you have to add in for you the velocity of the truck? Wouldn't it be c plus 15 meters per second? However, Maxwell was firm that light only had one possible speed, whatever it came from. There was one possible solution to this problem. Maybe there was something throughout space that let light travel through, was transparent, and was stationary. And maybe light travelled at one speed relative to this stuff that they called the ether. Then you would simply have to add or subtract whatever the source and the detector were doing relative to the ether. This idea was so widely believed that when Michelson and Morley set out to test it, everyone expected them to confirm its existence. They knew that only a very large speed would make a measurable difference in the speed of light, and they cleverly found a way to use the fastest moving object they could think of, which was the Earth in its movement around the Sun. If the Earth was moving through the ether, there should be an ether wind that would change the speed of light as we measure it in different directions, and an interferometer should be able to detect that. Now they knew that the Earth was orbiting the Sun in the east-west direction. Of course, they couldn't be sure if the Sun was also moving through the ether. So they repeated this experiment at different times of year. But they started with the assumption that at least sometimes there must be an east-west movement through the ether compared to north-south. So they took that if the Earth is moving at speed v relative to the ether, the speed of light for us would be c plus v in one direction and c minus v in the opposite direction. Now, if the interferometer was aligned with one arm running east-west and the other north-south, then that would change the path length in one arm relative to the other. Now, you don't have to work through the maths to work out the time interval, but you're welcome to do so if you want to. The result of working out the time for the return trip in each arm was that the faster Earth moved through the ether, the bigger the phase difference between the two arms. Now, a constant phase difference between the two rays means that there will be a stationary interference pattern. It would look just like the interference pattern you saw in the YouTube video before they started moving one of the mirrors. But if the interferometer was on a large rotating table and they rotated it through 90 degrees, the east-west and the north-south arms would be reversed. So the up and downwind arm should become the crosswind arm and vice versa. So the phase shift between arms should change and the rings should start moving as they did in the video when they moved one mirror forward. Michelson and Morley calculated how much the fringes would shift and they knew they could detect it. But in fact, the pattern didn't shift ever. They repeated it at different times of year in different latitudes with different equipment, and they never saw anything in the Earth's movement that altered the speed of light. This is the famous null result of the Michelson-Morley experiment. And it didn't quite end the ether theory, but it helped the acceptance of Einstein's theory of special relativity when he proposed that the speed of light was constant, regardless of the speed of the source or the speed of the observer. More of that in the next course.